Hello everyone, welcome to the video. Today we'll be studying about air refrigeration cycle. An air refrigeration cycle is a type of a gas refrigerant refrigeration cycle wherein the refrigerant is in the gaseous state. Here we have two types of air refrigeration cycles, an open and a closed refrigeration cycle. So this is the reversed Carnot cycle wherein the process goes from 1, 2, 3, 4 in the anti-clockwise direction. As it says the reverse Carnot cycle, a Carnot cycle goes in the clockwise direction. Here we have 1 to 2 and 3 to 4 processes are isentropic processes. As we can see that these are vertical lines and on the x-axis we have entropy, therefore they are isentropic. That means the entropy is similar throughout the process. And processes 2 to 3 and 4 to 1 are isothermal processes as they are horizontal lines and there is temperature on the y-axis. 1 to 2 is isentropic compression as the pressure increases, we can see here, and 3 to 4 is an isentropic expansion as the pressure is decreasing, and 2 to 3 is an isothermal heat rejection, we can see the arrow as it is pointing outwards. 4 to 1 is an isothermal heat addition as the arrow is pointing towards the system. This is the refrigerated space. Heat is extracted from here and it is made to enter to the system. Hence it is isothermal heat addition. All these processes it is a part of a Carnot cycle. Therefore all the processes are totally reversible. Now talking about the heat equations, we use the dq equals tds equation. We integrate on both sides, we get q2r. q2r can also be written as qh, therefore qh equals tds integration from 2 to 3, we get th into s2 minus s3. We integrate, there is no s, there is just ds, so integration of ds is s between the points 2 to 3, so it is normal integration. T is constant, t for qh process is th, T for the QL process is TL, we can see. Therefore QH equals TH into S2 minus S3 and QL equals TL into S1 minus S4. Now we know that work done equals QH minus QL. Therefore we have TH into S2 minus S3 minus QL, TL into S1 minus S4. Now we know that S2 equals S1 and S3 equals S4. We put the values, we get these two terms in common, so we take out these common values and therefore we have the W equals TH minus TL into W equals TH minus TL into S1 minus S4. Now we have the COP value. COP equals QL by W net. These two terms get cancelled and we have COP Carnot of a reversed Carnot cycle is TL by TH minus TL. Now this formula of COP is typically an idealized case COP. It cannot be used for each practical case. This is just for a reversible, or we can say a Carnot COP of an air refrigeration system. Now we'll talk about the practical cycle of an air refrigeration system. That is a Bell Coleman cycle or a Reversed Brayton cycle or a Joules cycle. The components used here are refrigerator, compressor, cooler and an expander. Now talking about the analogy, we have learned VCRS. In VCRS we had for heat addition to the system, that means for the QL, for the refrigeration effect we had an evaporator, and for the heat rejection from the system we had a condenser. Similarly in air refrigeration, for heat addition to the system we have a refrigerator, and for heat rejection from the system we have a cooler. So talking about that further, there are two types of Bell Coleman cycles. One, I would say Bell Coleman refrigerators. Now these are Bell Coleman refrigeration systems. This is a closed type. No, this is the open type and this is the closed type, wherein the main difference is this part. In closed type, the refrigerator is also connected to the refrigeration space and the heat is transferred using a brine solution, wherein here the refrigerator itself is the heat exchanger, wherein here there is a bridge between the refrigerated space and the refrigerator. Now talking about the open cycle first. From starting from 1, we are here, we go 1 to 2, that is a compressor, so we can see that the pressure is increasing. So here the compression occurs. From 1 to 2, we go 2 to 3. 2 to 3, there is a cooler. So we can observe that from 2 to 3 the temperature is dropping. Point 2 is here, point 3 is here, the temperature is obviously dropping. In 2 to 3 what happens is, we have a cooling water system. This is the hot compressed air at point 2. This is hot obviously. The compressed air from point 2 enters the cooler. It can be imagined as a shell type assembly, shell type heat exchanger assembly, wherein here the hot air passes through the tube, shell tube type, and here the hot air passes through the tube, and here in the background shell cold water is flowing through it. So cold water accepts the energy from the hot air coming from point 2, and the hot air coming from point 2 will get cooled down, and the cooling water which was passed through the cell will come out in a rather hotter temperature compared to its inlet. So it will accept the heat, and the temperature of air at point 3 will be comparatively cooler. Now it will be sent to the expander. So the cooled air at point 3 is sent to the expander to decrease the pressure, to expand it, and then it is sent to the point 4, which is the refrigeration point, and in point 4 to 1 there the refrigeration effect takes place. So we can see the various processes. Isentropic compression from point 1 to 2, process 1 to 2. At the end of the process, P2 is greater than P1, the pressure increases, obviously the temperature increases, but as it is a compression, the volume decreases after the compression. Then we see isobaric heat rejection at the cooling. At the cooler, we have isobaric heat rejection. At same pressure, the heat is rejected from the hot air to the cooling water. Then we have, and the formula goes Q23. The heat rejected equals Q23 equals Cp into T2 minus T3. It is simple mathematics. There is the temperature difference. Then we have isentropic expansion. Isentropic expansion takes place in the expander. Then we have isobaric heat addition that takes place in the refrigerator. Now you would say that what does heat addition mean? Heat addition means heat is extracted from the refrigerated space and that heat is added to the system. Heat addition does not mean that the heat is added to the refrigerated space. Heat addition means that heat is extracted from the refrigerated space and heat is supplied to the system. Similarly, analogously, we can say that in our room, when we turn on the AC, the heat is extracted from our room and it is thrown out from our room to the atmosphere. So the atmosphere is the part of the cycle, the surrounding, the ambient, and the refrigerated space is our room. Please catch the analogy correctly, don't get confused. Now we'll talk about the equation, the QL, the RE, the refrigeration effect. Q4 to 1 equals Cp into T1 minus T4, or rather T4 minus T1 to get the values positive. Now we have work done obviously equals QH minus QL. QH equals Cp into T2 minus T3 minus Cp into T1 minus T4, taking Cp common, and so the Cp gets cancelled out. While taking the COP, this taking Cp common, this Cp and this Cp gets cancelled out. We have the COP T1 minus T4 divided by T2 minus T3 subtracted by a bracket of T1 minus T4. Now taking T4 common in the numerator and T3 common here and again T4 common here. So we get the following expression. Now in an isentropic process we have the identity that T2 minus T1 equals P2 by P1 whole power to gamma minus 1 by gamma. Now gamma is the isotropic index, or we can say it is the ratio of Cp by Cv. So we can say that T3 by T4 equals P3 by P4. So we can also say that process 3 to 4 is also an isentropic process. So we know that as 1 to 2 is an isentropic process, we know T2 by T1 equals P2 by P1 whole power gamma minus 1 by gamma. Similarly, T3 by T4 equals P3 by P4 whole power gamma minus 1 by gamma. Now we know that P2 equals P3 and P1 equals P4. Here we can see P2 equals P3 and P1 equals P4. So substituting the values, we can also see that this P3 by P4 can be replaced by P2 by P1. And then we can say that these two terms are totally equal. So we wrote T2 by T3. So we write T2 by T1 equals T3 by T4. This is equal to this. Sending this value here and this value here, we get T2 by T3 equals T1 by T4. We did so that we can introduce this value equal to here. We have T2 by T3 here. So we can put T1 by T4 in place of T2 by T3. And therefore, putting the values, we can write here T1 by T4 minus 1. So we can take these two terms in common. So we get T3 minus T4 into T1 by T4 minus 1, and above we had the terms as it is. These two terms gets cancelled and we have T4 by T3 minus T4. Taking T4 into the denominator, we get 1 by T3 by T4 minus T1. Therefore, we know that T3 by T4 equals P3 by P4 as we have written above here. So we put the value of T3 by T4 here and we get 1 by P3 by P4 into P3 by P4 raised to gamma minus 1 by gamma minus 1. Now P3 by P4 equals Rp, or P2 by P1 also equals Rp. Rp can be called as the expansion ratio or the compression ratio. If we call it the expansion ratio, it takes place between 3 and 4, and if we want to call it a compression ratio, then it is considered between 1 and 2. But in such cycles, the expansion ratio and compression ratio is said to be equal. So hence we derive the COP and we have understood the working of a Bell Coleman cycle. Thank you very much.